Imagine standing in a lab on New Year's Eve, but the countdown comes from a pulsar timing plot instead of a wall clock. You are shoulder to shoulder with people in hoodies and wrinkled button-downs, everyone pretending the holiday exists while monitors glow like aquarium glass. The room smells like burnt coffee and overheated plastic. A printer chugs in the corner, spitting out perforated paper with little black marks that look like a lie detector test. Look at the screen. Each pulse lands like a tick, clean, spaced, obedient. The plot is a heartbeat that behaves like a metronome. Someone taps a pen against a mug, matching the cadence without thinking. You feel the comfort of repeatability settle over the room, the way gravity settles dust. But then, one tick lands wrong. Not. A bit off. Not. Maybe a calibration issue. Wrong in the way a safe door feels wrong when it is open to the air. The pulse arrives early. The line on the plot takes a tiny step it is not supposed to take. A glitch. A stutter. The old model says the star's crust is rigid enough to keep time. The data says the crust just lied. You see the faces tilt closer to the screen. Conversation stops as if the building loses oxygen. A calendar on the wall flips in someone's mind, last year's glitches, the paper that claimed a mechanism, the neat narrative everyone recites at conferences. You watch that narrative start to fray. Outside, the city prepares fireworks. Inside, the universe prepares an alibi. The plot keeps scrolling, indifferent. Another pulse lands. Then another. The timing residuals do not return to normal. They settle into a new normal, like a suspect changing clothes and insisting nothing changed. It is subtle. It is deadly. You see Rowan K. Mercer at the board, quiet, still, not performing. Chalk rests between fingers. Not a lecture stance. A crime scene stance. The question hangs in the air, what kind of solid changes its spin in an instant? You move closer to the workstation. The pipeline runs again. The fans inside the computer whine up, a thin mechanical breath. Someone mutters, "Bad ephemeris," then pulls up a different file. Another person opens the calibration directory, as if rummaging through drawers for a missing key. Look at the data reduction window. Numbers update. A progress bar creeps. A familiar ritual tries to cleanse the anomaly. But every correction makes the glitch sharper. A baseline subtraction removes nothing. A new dispersion measure fit refuses to flatten the curve. The residuals keep that step. It is there like a footprint in wet cement. You hear the chalk squeak, short, irritated strokes. Equations appear, get circled, get crossed out. The board fills with symbols that resemble a courtroom transcript. Torque, moment of inertia, crustal strain. The room tries to reframe the stutter as something respectable. But the star refuses respectability. Therefore, the search turns from how to clean the signal to what evidence the signal hides. A second monitor shows a different case file, a magnetar flare from months ago. The light curve spikes like a scream. The afterglow tail refuses to cool the way it should. You watch thermal models run, colored lines gliding over data points. But the models miss. The flare energy looks too large. The afterglow cools too slowly. The curved slope keeps bending in a way normal crust does not forgive. Someone tries a different conductivity. Someone tries a different heat capacity. Someone tries a different composition. But each tweak fixes one corner and breaks another. Therefore, the feeling in the room shifts. The data is no longer a number problem. It is a witness. And the witness keeps insisting on a detail the story cannot accommodate. You notice the soundscape, the low hum of HVAC, the occasional click of a keyboard, the soft plastic rattle of an empty water bottle rolling when someone nudges it. Even the air feels tense, dry, warm, slightly metallic from electronics. The lab lights make everyone look a little pale, like people who have been awake too long. Rowan points at the glitch plot without speaking. The gesture is small but final. The line on the screen is a door. The handle is turning. Look at the glitch again. A neutron star is a city-sized object with mass that shames the sun. It spins so steadily that it becomes a cosmic clock. People use it to test gravity itself. The crust is supposed to be a rigid shell over a superfluid interior, a tidy two-layer story. But this glitch arrives like a crack in the tidy story. If the crust is rigid, it should store stress and release it in starquakes, fine. That is the classic explanation. But the size and timing of this step, the relaxation afterward, the way the spin-down rate shifts, it looks like more than a brittle snap. Therefore, the suspicion grows, the crust is not what the word crust makes you imagine. Someone brings up a simulation, dense nuclear matter at subnuclear densities. The picture is grainy, a false color map of density that looks like weather radar. Blobs appear, merge, stretch. But the blobs do not stay blobs. They elongate into rods. Rods flatten into sheets. Sheets warp. The pattern is too organized to be a liquid, too strange to be a crystal anyone learns about in school. A junior researcher laughs once, short, nervous, because the shapes look like a joke. Rowan's voice does not fill the room like a teacher's. It lands like an investigator placing an evidence bag on a table. "Look at this," Rowan says. "Not nuclei." On the board, Rowan draws two regions, one labeled nuclei, one labeled not nuclei. The chalk makes a dry hiss. A line divides the board like a border on a map. But then the chalk stops. Rowan's hand hovers. The pause feels like a held breath. Then Rowan sketches shapes that do not belong in a textbook, parallel sheets like lasagna, tubes like spaghetti, bubbles like Swiss cheese. A lattice that refuses to commit. Nuclear pasta. Not metaphor. Architecture. You watch the room's posture change. Someone sits forward. Someone's eyes widen as if a new room becomes visible behind the old one. Because suddenly the cooling curve is not wrong. It is a report. If the crust contains regions of this semi-ordered matter, heat does not flow like it does through a neat crystal. It gets trapped in weird ways. It leaks along channels. Conductivity becomes directional, like a city with one-way streets. But the best part, also the worst part, is what that implies for stress. A lattice of sheets and tubes does not break like granite. It deforms sticks on sticks. It can pin superfluid vortices. It can hoard angular momentum in hidden ways. Therefore, the glitch stops being random. It becomes a crustquake in a structure that is neither solid nor liquid the way the mind wants to categorize. Now look at the magnetar case again. Magnetars were magnetic fields so strong they stop being a property and become a force of architecture. Field lines do not decorate the star, they wrench it. You see a diagram on the screen, magnetic field lines twisted, anchored in the crust. A flare happens when the twist snaps, like a rubber band giving up. But a crust made of nuclear pasta does not respond to that wrench like a simple elastic shell. Therefore, energy injection and thermal relaxation look different. Therefore, the afterglow cools too slowly because heat cannot escape cleanly. Therefore, the flare energy budget looks too large because the crust stores stress and releases it through a complicated, semi-ordered network. The room is quiet in the way a courtroom goes quiet when a witness says something no one expects. Someone tries to object. "But pasta is a joke name." Rowan does not argue. Rowan points again, this time to the simulation frames. Sheets. Tubes. Knots. Phase boundaries that move like continental plates. You feel the shift, the name does not matter. The geometry does. Because at those densities, nuclear forces and Coulomb repulsion negotiate. Too close and nuclei merge, too far and they separate. Pressure forces compromise. The result is not a sphere. It is a compromised shape. But compromised shapes have consequences. Therefore, timing glitches, crustal oscillations, and thermal afterglows become one story instead of three unrelated mysteries. The lab returns to the pulsar plot. This time, the residuals are not treated like garbage. They are treated like handwriting. You watch someone overlay models that include vortex pinning in a complex lattice. The fit improves. The step looks less like a mistake and more like a signature. But there is still a problem. The relaxation timescale, how the pulsar returns toward its previous spin-down behavior, does not match a single reservoir. It looks like multiple components exchanging angular momentum. Therefore, the interior must be layered in a way that is not just crust and core. The conversation becomes sharper. Not louder, sharper. Words like entrainment appear. Shear modulus appears. Impurity parameter appears. Anisotropic conductivity. Each term lands like a flashlight beam sweeping across the floor. You are right there as the beams converge on a shape. The crust is a structured, messy, partially ordered region with pasta phases, defects, and pinned vortices. Look at the chalkboard now. Rowan draws a cartoon of a neutron star as layered rings. The outermost layer is thin compared to the whole star, but thick compared to any human structure. Rowan shades the inner crust region and marks it with little squiggles representing vortices. But the vortices do not float freely. They pin. They snag on the pasta. They store rotational lag between the superfluid interior and the crust. Therefore, when enough stress builds, unpinning happens in an avalanche. Angular momentum dumps into the crust. The star spins up. The glitch appears. You can almost hear it, not a sound in air, but a conceptual sound, a locked gear suddenly slipping. Now the magnetar flare overlay returns, and the pieces click into place. A crust under magnetic torque experiences slowly growing shear stress. The pasta phases deform and resist in complicated ways. At some threshold, the structure yields, fractures, rearranges, slips. But yielding does not mean simple cracking. Therefore, the flare does not simply break the crust, it reorganizes it. It releases stress in steps, excites oscillations, traps heat, and changes conductivity pathways. You watch the light curve again. The spike is the scream. The tail is the aftershock. The too slow cooling is the rubble settling. Outside the lab, voices count down. 10, 9. A faint cheer leaks through the windows, muffled by glass and distance. Inside, the countdown is a different kind. You see someone refresh an email thread. An observing team confirms the glitch in a separate pipeline. Another message arrives. The glitch coincides with a subtle change in pulse profile shape. The star's magnetosphere shifts too. But coincidence is a dangerous word. Therefore, the suspicion becomes a hypothesis. A crustal event couples to the magnetosphere, changing emission geometry. The clock not only stutters, it changes its face. You feel the lab as a physical place. The chair fabric scratches under a shifting posture. The air tastes stale. A microwave beeps somewhere, ignored. Someone opens a fresh bag of chips and the smell of artificial cheese mixes with coffee. It is mundane. But the object on the screen is not mundane. A neutron star compresses matter beyond ordinary categories. At that pressure, atomic structure is not an identity, it is an option. The star is a physics laboratory with no safety rail. Therefore, every anomaly is potentially a new phase of matter announcing itself. Rowan erases part of the board with a sleeve. Chalk dust blooms, floats in the light like tiny comets. New lines appear. Two competing timescales get written, one for magnetic stress buildup, one for vortex unpinning. Another set for thermal diffusion, another for mechanical damping. But the key is that these timescales intersect. Therefore, the star produces a family of events that look different to telescopes. Glitches, bursts, flares, quasi-periodic oscillations, but share a crustal origin shaped by pasta geometry. You see the idea forming like a suspect's outline in fog. Someone brings up quasi-periodic oscillations observed after giant magnetar flares. Frequencies show up, tens of hertz, hundreds of hertz. The debate begins, crustal modes, Alfvén modes, coupled oscillations. But a crust with pasta phases has different elastic properties. Therefore, mode frequencies shift. Damping changes. Coupling to the magnetic field changes. The oscillations become a seismology tool. Look at the plot of frequencies. Each peak is a bell ringing inside a star. You can almost feel it through the floor, not as vibration, but as implication. A city-sized bell with a lattice of lasagna and spaghetti inside. Now the room tries to quantify. Numbers replace metaphors. The shear modulus of the pasta region is estimated. The viscosity of the nuclear fluid is considered. The impurity parameter influences electron scattering. But the parameter space is huge. Therefore, the lab begins to treat the pulsar and magnetar as constraints, not curiosities. The glitch size constrains pinning strength. The cooling tail constrains conductivity. The QPO frequencies constrain elastic structure. Multiple datasets triangulate a hidden interior. You watch a triangulation happen in real time, like locating a gunshot by timing differences across microphones. A new plot appears, thermal conductivity versus density. Another, neutrino emissivity. Another, heat capacity. The curves diverge depending on whether pasta exists, and how it is arranged. But nature chooses one arrangement. Therefore, the universe becomes a selection mechanism. The star's behavior picks the curves that survive. Rowan points to a region on the conductivity plot where anisotropy matters. Along sheets, electrons flow easier, across sheets, they scatter. Heat flows like water in layered rock. But layered rock can trap pressure and produce quakes. Therefore, layered nuclear rock traps stress and produces star quakes, which produce glitches, which produce magnetospheric shifts, which produce observational signatures. Everything begins to chain. Outside, midnight hits. A distant roar rises. Fireworks crackle. Light flashes across the window glass in brief, bright bursts. Someone in the lab smiles without turning away from the monitor. Look at the fireworks. The bursts are structured, rapid rise, slower fall, flickering tail. But out there, it is chemistry and air. Therefore, the mind snaps back to the screen. Out there is celebration, Up there is an object doing something similar with gravity and nuclear matter. A neutron star does fireworks too, brief, bright, structured bursts, but the fuel is magnetic stress and the medium is pasta crust. You step closer to the window. The glass is cool. The night air outside looks clean compared to the lab's stale warmth. But the sky does not show the neutron star. Therefore, the realization lands: most of the universe's most extreme matter is invisible to eyes. It is inferred from timing residuals and cooling tails and frequency peaks. It is detective work. You turn back to the room. The team looks like people who just found a hidden room in a familiar house. Rowan draws one more thing, a simple phrase on the board. Matter forgets its shape. Not poetic. Literal. Under enough pressure, the concept of a nucleus, as a tidy ball, becomes negotiable. The nucleus stretches, merges, forms sheets. The boundary between inside nucleus and outside nucleus becomes a labyrinth. But forgetting shape does not mean chaos. Therefore, the matter adopts new order, an order defined by competing forces and brutal constraints. Now the glitch on the screen is not just a stutter. It is a message from a regime no laboratory on Earth fully recreates. A neutron star broadcasts the mechanical properties of nuclear pasta through its timing. But the message is encoded. Therefore, the job becomes decoding, linking each observable to a physical knob inside the star. The lab starts listing: glitch amplitude, pinning strength, crustal moment of inertia, superfluid coupling, relaxation, mutual friction, temperature, defect structure, flare tail, conductivity anisotropy, heat capacity, magnetospheric currents, QPOs, elastic modulus, magnetic coupling, layer thickness. You see the list grow. The case file thickens. Someone asks the question that always lurks. Is nuclear pasta real, or is it a modeling artifact? The room does not flinch. The question is not hostile, it is necessary. Look at the evidence pile. Independent simulations, different nuclear interactions, different numerical methods, many still produce pasta-like phases near the crust core boundary. But simulations can agree and still be wrong. Therefore, the argument turns observational. If pasta exists, it should leave fingerprints, reduced neutrino cooling in certain regimes, altered crust thickness effects, modified glitch statistics, specific thermal relaxation profiles after outbursts. You watch people compare predicted fingerprints to data from multiple sources: isolated cooling neutron stars, transiently accreting systems, magnetars after bursts. Each dataset is a partial witness. But partial witnesses can corroborate. Therefore, confidence grows, not certainty, but the kind of confidence that comes from many independent constraints pointing toward the same hidden architecture. The mystery is no longer, why does the pulsar glitch? The mystery becomes, what is the crust made of really? Look at the phrase, crust. It conjures bread, earth, something brittle. But the neutron star crust is a spectrum. Therefore, crust becomes a shorthand for an ecosystem of phases: ions in a lattice, neutrons, superfluid, pasta structures, defects, magnetic stresses, and electron seas that carry heat and current. You see how language fails and gets patched with metaphors. Pasta, cheese, lasagna layers, spaghetti rods. But the metaphors do not trivialize. Therefore, they become handles for something otherwise too alien to hold. A new run finishes. The model, including pasta-enhanced pinning and anisotropic conduction, overlays the data. The fit is not perfect. But it is better. Therefore, the room exhales in a way that is almost silent. Not victory. Direction. The glitch stands there, still mysterious, but now it is a signpost instead of a dead end. You notice the human layer of the scene: tired eyes, cold pizza in a box, a holiday hat someone wears ironically. The ordinary keeps trying to reclaim the night. But the extraordinary keeps winning. Therefore, the conversation drifts from this single glitch to a population. How many glitches does this pulsar show? Do magnetars glitch differently? Do older pulsars show different behavior? Does temperature matter? You see a scatter plot appear: glitch size versus spin-down rate. Points cluster, outliers stand apart. But the outliers are the most interesting. Therefore, the outliers become targets. Each outlier is a star whose interior might be arranged differently, whose pasta might be more tangled, whose magnetic field might torque more violently. Look at the sky map on another screen. Dots mark known neutron stars. Each dot is a collapsed core, a remnant of a supernova, a gravitational well with an outer shell of exotic matter. But the dots look identical on the map. Therefore, the only way to tell them apart is by listening, timing, spectra, bursts, cooling. The lab listens. The case returns to first principles, not as a lecture, as a reenactment. A neutron star forms from a collapsing massive star. The core compresses. Electrons and protons combine into neutrons. Gravity squeezes everything until the pressure is unimaginable. But gravity does not negotiate politely. Therefore, matter rearranges into whatever minimizes energy under constraints. Nuclear attraction wants clumps. Coulomb repulsion wants separation. Degeneracy pressure resists compression. Magnetic fields impose direction. The result is a layered interior where shape becomes emergent, not assumed. In that interior, pasta is not a quirky footnote. It is a natural consequence of competition between forces at extreme density. But consequences show up at the surface. Therefore, a timing glitch on a screen in a quiet lab becomes evidence of geometry deep inside a star. Look again at the beginning of the night, the tick-tick-tick of pulses. Now look again at the stutter. It no longer reads as an inconvenience. It reads as a fracture line through a simplistic worldview. The star is not a perfect clock. It is a clock with gears made of semi-ordered nuclear matter under magnetic torque. But a flawed clock is more informative than a perfect one. Therefore, the glitch becomes the universe's way of letting humanity audit its hidden materials. The room settles. Not into boredom, into focus. Plans form. Additional observing time gets requested. A proposal draft appears. Someone mentions a new telescope backend that improves timing precision. Another person mentions X-ray monitoring after the next burst. But the star does not schedule its secrets. Therefore, readiness becomes part of the science. Instruments waiting, pipelines ready, hypotheses sharp. Outside, the fireworks die down. Smoke drifts through streetlights. The world begins its new year. Inside, the new year begins in a different way, a new model of matter. Not matter as a fixed menu, solid, liquid, gas, plasma. But matter as a negotiation with pressure, temperature, and fields. Now the conclusion arrives as a narrative sequence, like closing a case file. The synthesis. Under enough pressure, matter stops honoring familiar shapes. It does not become featureless. It becomes structured in alien ways, sheets, tubes, knots, architecture built from nuclear forces. A neutron star crust is not simply a shell. It is an active, semi-ordered machine that stores stress, traps heat, and releases time itself in sudden steps. The mirror. So next time you look at a clock, on a phone, on a wall, on a microwave, notice how much trust sits inside that steady ticking. Somewhere in the sky, a city-sized star keeps time too, pulse by pulse, until it can't. That failure is not a malfunction, it is a clue. It is the universe revealing the materials it uses when it runs out of room. The next question: if a neutron star crust can forget its shape and still build new order, what other, fixed, categories, inside atoms, inside planets, inside living brains, turn out to be negotiations under hidden pressures?